back to the final talk of this morning's session. I'm pretty sure that Finn's going to keep the schedule since she's rushing off to catch a taxi to catch a train to go to London to give another talk this afternoon. So we'll keep the questions limited to no more than 15 minutes each. Prediction using side information, whatever that may be. Finn.
Thank you. First, I'd like to thank the organizers for inviting me. And the side information, I work also with engineers, was try to give a vague title when I didn't know what exactly I was going to talk about. So this is more like from communication. And so this is work based on two actually different pieces of works which can be covered by side information. And with former student Peng Zhao and current student Guilherme Roja. And the second part is with another student, Vince Wu, who actually is here, will answer all the hard questions on that part. And so here's the roadmap for my talk. And we heard a lot about L1, many wonderful talks about it. And I will say that sparsity is one kind of side information, and I will go further to general penalization method, which has connection with the Bayesian, maximum posterior. And the first about talk would be try to build up some penalty based on side information on grouping and also on hierarchical. So grouping has been done before, but our framework on campus is that and also can build in hierarchy information between the predictors. And the second part is very much ongoing research. And the result, Vince was still doing result this week while he was already on travel. And so would be really a welcoming inputs from the audience since we have so many bright minds here. And the second part is try to use unlabeled data and connect to the two talks yesterday afternoon on semi-supervised learning. And it's motivated by problem in neuroscience, which I've been collaborating, I spent last year actually in the lab. And we now try to build something in from the unlabeled data. But in the end, we're not so convinced we're doing semi-supervised learning or just regularization. But even we went in thinking there might be a better way to use the unlabeled data. So we have some experimental preliminary results on that. So I'll try to be a little fast on the first part because I'm more excited about the second part since it's more current work. And this, I'm sure, have been said many times that we have lots of data, lots of large P, and N could be small, but in other engineering applications, N could be large too. And we have opportunities, like previous talk, to find new scientific facts. And this is just a standard setup. I use Z to have the couple of Xi and Yi. And Xi is a p-dimensional vector. And the first part of the talk also has Yi as the classification case, but the second part is more regression. An example, I'll just give you some sense of my P and N. In the second example, my P is like 11,000, my N is like 2,000. Okay, so that's the dimension. And we all know that if you just do empirical minimization of loss, often you have ill-posed computational problems, and that's very much related to bad prediction. And regularization recently has been used in many different ways to improve prediction. And you have penalization. Actually the ridge or L2 penalization can be traced back to 1940s when Tikhorov was doing the integral equation, tried to deal with numerical stability. So there's clear connection to computation. And the model selection appeared in the 70s, really aimed for sparsity, but was kind of hampered because the computation cost. And then the modern fix to the problem is L1 because it's nice convex optimization. So it's very much connected with computation. And the second way of doing, oops, I'm not doing right. Okay, the wrong key. And boosting, I've also worked a lot on use early stopping to bring in regularization. And the tuning parameter itself is the number of iterations itself is very computational, right? It's convergence analysis and when you stop. And it appears in neural nets, and now it's used in boosting. And then we heard in Mike's talk yesterday that you have hierarchical modeling and very much how you choose these priors and different pieces of this modeling is very much also related to computation consideration. So L1, I think I can just skip, right? I already heard a lot. So let's just go to the general penalization. So I use T beta as a general, could be the L1 penalty, and lambda is the tuning parameter. And if we go beyond the sparsity at the individual levels, that we might be able to take into account structure information among the predictors. For grouping, that's for one side information. And especially when for P much larger than N, I also want to argue that even you don't have this information, this brings regularization, and just for prediction purposes needed. Even a lot of the grouping might not be there, but just for actual regularization, it helps. For example, genes belong to the same pathway. You might want to say that they should be in and out together, and you might make up categorical variables, from the same, use dummies for the same categorical variables, and they should be in and out together. Maybe polynomial terms for the same variables. And you might have different measurement of the same variable. That's for the grouping motivation. And for hierarchy, you might know that, for example, in ANOVA, you want the main effect terms first. And if the interaction terms are in, then you want to make sure the main effect is also in. So that's a hierarchy. And in wavelet, analysis, you want to do the same thing. The kind of descendants of the higher level, the low level, the coarser level coefficients should be in, and then will motivate the coarser level should be in there too. And maybe there's something about also Markov chains, which we haven't explored a lot. So I want to first mention, actually we started on this work, working on some graphical, some work follow up on Peter's work in the using lasso for graphical model selection, and we want to put in a constraint of two ways of calculating the same beta should be the same. And then we start doing this penalty stuff, and then realize that there were other people working on the same topic, for example, elastic net and Galasso, and also the block by structure regression. But we were going for a more general framework and also having the hierarchical selection in mind. So for this class of penalties, which I'll show you, which is a combination of different L gamma norms, you have convexity, and you have piecewise, you have some path following algorithm, in some cases very similar to Lars, and in other cases it's more like boosting, which can run this penalization at least pretty straightforwardly. I wouldn't say fast in all cases, but pretty straightforward to program. And the group, I'll come back to that later. Right now, we assume you know the structure, but in the simulation, we actually explored it a little bit to do data-driven structure. But it's not completely data-driven yet. There's something we didn't deal with in this paper. And the idea is really combining different L gamma norms. So we see a lot of the L1 penalization, right? And then you have this solution path. For people who are not in this solution path, let me just explain what's being plotted here. So you have a penalty L gamma norm defined like this. And for gamma larger or equal to 1, you have a convex optimization problem. And when you have different lambdas, then you have a different solution. And suppose beta is 10-dimensional. This is the data from the diabetes data of the Lars paper. And then for each lambda, you're going to have 10 estimates. So you look this way. And what's being plotted on this direction is the L1 norm of the solution, because the solution is overachieved at the boundary. Okay? So when you move lambda, you effectively also moving the constraint on L1, and you create a path. So this curve corresponds to one of the betas. Here you have 10 betas. Okay? So this is L1 penalization. Of course, the L2 really was in that in the numerical calculation, like computation paper in 40s, but formally it's called RAGE in 1970. And then 1993, this Frank and Freeman paper considered general gamma called bridge, and Lasso, the name came from 1996 paper, but there were earlier works by Chen and Donahoe on basis pursuit. And then in the special case gamma less than 1, which we're now concentrating on that, there's a scared by Fan and Li. And when you have L2, you can see that you lose the sparsity. Right? It's kind of all departed from 0 pretty much. It's a shrinkage kind of across different betas. But the interesting case, which will take a lot, especially computationally in CAP, is the L infinity. L infinity, geometrically, you can see it's very similar to L1. It's like the dual form. And the constraint imposed, because the solution will be on the corner, is imposing equality between the betas in the same group. Okay? So now I only have 2 dimensions. I'm basically going to want to be there. So you can see they kind of try to stick together, and then they separate. Okay, so this is more general. And so here's the recipe. We have the same, say L2 doesn't have to be L2, can be generalized linear models, a convex loss function. And now we're going to have group structure given. So say x1, x2, x2, x3, and so forth. And within the group, we're going to use gamma 1 norm. And in the implementation, we take the gamma 1, gamma 2, and gamma k all the same. Right? But in theory, you can vary that too. And then you have an overall norm, which will put them together. Okay? So you basically take square root, like beta 1 squared plus beta 2 squared, and square root of that, and then for the group I just mentioned, and that basically is the grouplet suit of Yuan and Lin, but we're considering the more general case. Since we started actually L infinity, but the special case L1 have been L2 have been considered. And the groups may overlap. For this is kind of new for selection. And there's a Bayesian interpretation for the non-overlapping groups. We don't have a good one for the overlapping groups. So because it's really penalized minimization, the penalization, when you do the exponentiation, is kind of a prior, and then you're doing maximum posterior. So the prior corresponding to this, the cap penalty is you first get a norm following something like generalized double exponential family or generalized Gaussian. Right? In engineering literature, it's called generalized Gaussian. After you have the non-fixed sample from this, and then you take uniform on the sphere given by the norm. Right, that's the prior within the group. Okay, so cross group, you're doing this generalized Gaussian prior for gamma 0 equal to 1 case. That's the case we simulate. You have double exponential, and giving the norm, you do uniform distribution on the sphere given by the norm within the group. And let's just see. So we usually take gamma k larger than 1 within a group. So we want to force similarity. As I said, I want to introduce more regularity than lasso to taking into account the prior information if there is, otherwise just for regularization. Because when P is really large, lasso sometimes not enough. And then you basically, when gamma k larger than 1, you're basically enforcing that all the variable in the group to be included and excluded together. And Jiju and I think Lavina in Michigan have, they feel like this is too restrictive. So they try to give more freedom to this, but then end up with a non-convex optimization. So there's a trade-off. You can be more flexible, but the computation will be harder. But this is for a lot of work. And if you take gamma 0, the overall norm, to be 1, then you're enforcing sparsity at the group level. So it's very much related to lasso. And this is a case with gamma equal to 2, considered by Yuan and Lin. And this is kind of in 3-dimensional case, called beta 1 and beta 2 in the same group, and beta 3 in its own group. So you can see that you have some edge, but then within beta 1 and beta 2, you have kind of this L2 constraint, circular constraint. Okay. And how to build in hierarchical structure with this cap. Let me just show you a simple case. You want to have beta 1 and beta 2. And you want to make sure that if beta 1 is dominant one, you want to make sure that if beta 1 is in, and then beta 2 come in after. So you make up these overlapping norms, take the beta 1, beta 2 infinite norm, and beta 2. So somehow beta 2 is doubly penalized, and therefore it's harder for beta 2 to come in, and then you create this polytope. So I was just talking to Jerry yesterday that some of his results can be generalized to this case. And then you're kind of preferring these vertices. And on all these vertices, beta 1 comes in before beta 2. Okay? And this is just it's a generalization to say that this is a directed graph, and I can enforce this hierarchical structure by a general directed graph and just put a infinity norm or gamma k norm for any node and all its descendants and put them together and force that overlapping group. And this is a simple case you see already. It's hard to do it's harder. I can do 3-dimension, but opt for the easy one, only the 2-dimension case. So in general, you have given a hierarchical tree, you can enforce that in this optimization framework. Of course, hierarchy has been dealt a lot in the graphical model literature. So how to solve this optimization problem, again, more in the past Pauling sense, you could do proxy algorithms, and there are 2 general algorithms by Rosette. He basically goes to second order, and by the connection of boosted lasso or B lasso, you can do general kind of boosting-like steps, gradient-like steps to do any convex loss function with penalized loss. Okay, it's pretty simple, but it's not always fast. It sometimes can be very slow because it's very simple to program. So it's kind of a good protocol algorithm. Try out some data, see the feasibility of the method, but because just like boosting, is taking small step can take a long time. But in the special case, as I point out, the geometric similarity between L1 and L infinity, when you have this L1 and L infinity combination means L infinity within the groups and L1 over the groups, then you can do exact algorithm for tracing the regularization path. Okay, so we have an algorithm I for infinity, grouped selection, we call ICAP. The student was so very excited to think about this name for obvious reason with the iPod stuff. And hierarchical selection, we have a high cap. Okay, so my students were better with names than me, so they were very excited. And for tuning the parameter, you can do cross-validation just like we do for, and we also explored something we quite like. It's called corrected AIC. And we generalized some idea from Zhou et al. The degree of freedom for ICAP, because ICAP is very similar to lasso, so you can do a good counting of parameters. And in our simulation, this is a lot faster because you don't have to do many runs, and you have very similar result as cross-validation. But this idea of model selection appeared in Peter's work, and we did something too with Peter. So, and other people have done it too, using model selection to cut down on the cross-validation cost. And I just want to show you one example because I want to move on to the second part. The hierarchical case, because I think it's our contribution is, I think nobody has done this before. The grouping case, we did more generalization, but other people have done special cases. So for the hierarchical selection, so this is a simulation with 3 main effects, and we're only looking at pairwise interactions. And the simulation we did no interactions, and then weak interaction, and moderate interaction, and very strong interaction. And for the very strong interaction, actually the signal-to-noise ratio is higher than the first 3. So we want to see that by enforcing this hierarchy, saying that if the interaction is in, then these 2 have to be in, whether we can gain more than just doing lasso. So this is for model selection. in the no interaction case, did I give you the, yeah, so we have 50p is 55, and we have n is 121.
Excuse me, are you assuming sigma is known in that? Or is the estimate the same for all?
In this, in our calculation, we don't need sigma.
Okay, so the column sigma.
It's just for the simulation. It's for the simulation. We just chose it. I think the student was trying to make the signal to noise ratio, and somehow that gives a good matching. There's no particular reason why 3.7. So we don't need this in our algorithm, but it's just the simulation setup. So if you see that the all of these different versions of CAP, this is basically Yuan, Lin's, Gila, Su, and this is, it kind of cut down the model error by half in the no interaction and weak interaction. And for the moderate interaction, you see what happens is that the Su are recognized when the interaction instead will pick out those individual terms too. So this relationship helps more in the weak interaction case, and no interaction case is just more regularization. And for the strong interaction case, they've become quite comparable because Lasso was able to pick up them individually too. Okay, but it didn't seem to hurt. And we did a lot more simulation in the paper, but I won't go here. Here's a general kind of qualitative summary of the simulation results. Well, I guess I deleted a slide, which, well, I'll just tell you that there should be another slide on the summary. Last night I was deleting slides and deleted the one I shouldn't have deleted. So maybe I knew what Peter was going to say about giving a short talk. And usually you see a non-trivial reduction of model model error. And in terms of sparsity, if you count the terms, it gives more because we'll drag in other ones in. But if you do the degree of freedom, it gives you sparser models, right? So it depends on how you count. If you just count terms, then the CAP group them together will drag things in together, therefore actually more terms. But if you count it, use the degree of freedom we develop based on the Zhou work, then it's sparser. And the argument, and in terms of how to select the groups for the hierarchical simulation, we did give the structure in the model. But for the grouping, we did a kind of a combination. We know the number of groups, so we tried a few variations in the number of groups, like the same size, double the size, half the size, and use hierarchical clustering to give the groups. And then that's how we did it in the simulation. But it's not completely adaptive because we did give the number of groups close related to the true. But in some sense, we can add another one too. We haven't done that. Just the paper was going too long. We had to finish, so we just stopped there. And for the AIC, C, and cross-validation, we got very comparable results. And AICC is a lot faster. So AICC was used for a lot of the later simulations. Okay, so that's a summary. I think I want to emphasize the hierarchical aspect. And we have algorithms, general algorithms, and also especially for the L infinity case. Okay, so let me move on to the second part, which is very much fresh off the oven or still in the oven, depending on how you look at it, work. So this work, I spent last year at the Galan lab in Berkeley. The Galan lab is a leading lab using natural stimuli to stimulate the visual pathway of primates and humans. And before, I think this lab and maybe other lab, a lot of times people use very kind of controlled stimuli to trigger the visual pathway, like grating or bars. And a lot of the fMR work we see in the statistical community is also more psychoanalysis, like there's task-driven. You have somebody doing something and certain part of the brain light up. So I've seen, there are a lot of work on that. So this is a little different in the sense it's more into the estimation. So the lab traditionally was working on single neuron recordings and to use the natural stimuli in the transform domain and relate to the single neuron spike train. Okay, but recently they moved into fMRI data because it's easier. You have more data available and more spatially because single neuron, the lab is moving to multi-neuron but hasn't gotten there yet. So it's hard to have a spatial coverage. So this is a setup, a postdoc actually. All the data is from him so far because his brain is easier to register than other brains because registration is a problem. And he just lie there for hours and then he's looking at the screen through a prism of, I'll show you the images, natural images, and then fMR, a huge magnetic field is here, and then the particles in the bloodstream get lined up and give a signal. So this is not direct measurement of neural activities, but indirect. I mean, people argue how much relate to neural activities, but I'm just saying that we just try to relate to the fMR signals. Eventually, they're interested in the neuron activities. But right now, that's readily available technology. Okay? So this is the one piece of the natural stimuli the postdoc is looking at. And they crop the image to fit a so-called receptive field so that he doesn't get distracted with other parts. And they have a database of 11,000 images, all cropped like that. And they randomly select. So they have some now, they're going to collect data on natural movies cropped like that. But right now, it's randomly selected from this database image. And this postdoc, look at it, and then they have fMR signal. They did process fMR signals, and then we got the process data. I knew a little bit about how some PCA was involved. I haven't dealt with that part yet. But after the processing, you get pretty Gaussian signals. And for voxels, so each voxel is like a three-dimensional location in the brain. And because the image is a kind of ID from this database, doing voxels estimation together, at least more or less you do the same thing doing voxels independently. Okay, so that when you have free will movies, definitely you want to look at all the voxels together. So they don't just use the pixel values as predictors. In the low vision areas, still biological work and also work related to this ICA, or that to say that basically the early visions are like Gabor or wavelet-like processing, linear processing. So they build up their model first from low visions, but now also using the same feature extractions on the high regions of the brain. So they have this, the spatial frequencies is complex wavelet. You can see get faster for different frequencies and different orientations. And then they use a Gaussian envelope to get the Gabor wavelets. So that's the linear filtering. Okay. So at different locations of different pixels, they apply many filters. So it's an overall complete representation of the image. And then that's the filter stage. And then they did, actually the square shouldn't be there, it's a typo. That then they did just by empirically work better before they didn't do a log transform. They did a log transform, and now they have a feature vector. It's a little, bad notation because my xi before was index of data units, now indexing the different features. So it's that you have about 11,000 dimension. P is like 11,000. And then they have been, in the transform domain for the low vision area, they've been very happy with the linear model. This is also what's used for the single neuron, and they just use it for fMR and seem to work well. So that's what the current model. So you have P equal to about 11,000, you have about less than 2,000 training samples, but it's via IID. And they were pretty good that, they were one of the first that also use properly validation sample. Actually set aside 120 samples with, in the single neuron, they actually have repetitions. Do they have repetitions here? They also have repetitions here, 10 or 20. Yeah, so they have repetitions for these validation samples. and with the same features. And then they don't think they can match the magnitude because the different regime of lighting and all that. So they do correlation as the validation metric. Okay, so actually they don't touch it at all for this validation sample. They do selection, cross-validation all here with the training sample, this much, and then they do proper testing. Okay, so they're pretty careful, very much into the predictive methodology right now. And this is old stuff. I just want to motivate what we end up doing. So when we started on this, we were doing boosting and lasso, and also knowing this problem. So this is said before, right? So the just maximizing empirical loss function L2 is your post has computation or prediction problems, and we talked about ridge, and you can do pseudo inverse, or we see a lot of lasso, and it's very related to L2 boosting, and that's the preferred method in the Galan lab right now. So the history was like I've been telling them about boosting for until they 2 years before they or 1 year before they start working on that, and they Jack Galan just like, oh, we try everything, I don't think boosting will work. And then a postdoc of his rediscovered L2 boosting by himself. He was just refeeding of residuals, and then they fell in love with it. And then so we were doing B lasso at the point, just doing really the lasso version of boosting, and then they were very excited. And since boosting was so good, they did try it, but it didn't change much because the noise level was very high. So I think it's for single neuron data, but I think for this data, if you try lasso, I think you get very similar result here because signal noise ratio is not very high. So you don't take many back steps. So the difference in boosting and lasso is really to get exactly lasso, sometimes you need to take a backward step, not just forward step as in boosting. And you rarely take those steps. So they're basically giving very similar results. They tried that for single neuron and get very similar results. So they're sticking with boosting simply. And they do have this database, right? 11,000 is this unlabeled data. And so the question is, can we take advantage of this unlabeled data as in many other problems, which is readily available for this regression problem? And there's a collection of articles in a recent book called Semi-Superior Learning. And there's also a nice statistical science article, more from the statistical point of view by the Duke group, including Mike and Liang and Michael Hergy, just appeared. And basically, you need the marginal information, the marginal distribution X, in somehow relate to the conditional distribution of Y given X for the unlabeled data to be effective. And in the classification case, it's easy to see that you want the low density regions of the marginal distribution kind of coincide with the boundary, decision boundary, and then you're in game. So there have been a lot of, I shouldn't say a lot, the empirical studies for classification problem to show that unlabeled data is helpful. I haven't seen maybe just a lot of regression case yet. So we basically have a regression problem. And the question is how to take into account this unlabeled data. I'll show you that I'm not sure our first attempt is extremely successful. So there was earlier work by Brown basically pointing out the difference between fixed design, again the fixed design and random design are quite different. And for fixed design, you don't have much marginal information, therefore, don't need to worry about unlabeled data. But for random design, there's room. Okay, even in this, just look at the intercept, the 1990 Brown work. And back to OS, I'm just giving you a historical account of what we did, but might not be in the end right in the paper. So the least squares is really, you can see it as a plug-in estimator of this population version. And so our first thought was that maybe you can use the population covariance, assuming we have infinite unlabeled data, to improve estimation of the sample covariance. And at the time, we also, Peng actually was looking at some finance literature, and there was this nice paper of Ledot and Wolf to combine the sample covariance with another covariance matrix. So this is another way to regularization besides what I think Peter talked about, the banded different ways of regularizing the sample covariance matrix. I think I mentioned different Peters means different last names, but I will be more specific next time. And that in this paper, they were using a kind of factor model in finance, a parametric model, to argument the sample covariance. And we thought, well, just copycat that. If we put in the population covariance in our problem, what will happen? So we call semi-OIS. Okay, and of course we're interested in the p larger than n case. And of course, it turns out that this is related to, equivalent to a panelized least square problem with this as a penalty. This n is there just because we want easier writing, so we put the n there. It could be just lambda there. It's just a scaling. So this is like panelizing instead of L1 or L2 with the quadratic form with the population covariance matrix. And if you think this way in a Bayesian, it's kind of Bayes like max posterior. This is like not very natural after you have in this form. In the other form, we thought it was pretty natural, right? Putting the population. But this is only recently when I prepared the talk, we thought, well, actually, this is equivalent to this penalization. And you think about Bayesian way, then this is saying that suppose this is diagonal, right? You're kind of saying that you're putting, you're thinking that maybe the beta, because for the small eigenvalue directions, beta can be large, right? It doesn't seem to be the right thing to do. But nevertheless, that was later. So we wanted to do some calculation to see, compare with OIS. That was the easy, kind of benchmark to compare. And we're also picking up on random matrix theory. So we thought, well, something like that could help because sample covariance. So we're very much into the sample covariance random matrix theory when we started. And now we move into more, it's really actually penalization if you look at it this way. And if you assume that you have a Z comes from, it's a whitened version of your original predictor, and then you have this form for your we call semi-OIS. And then in general, you don't have to do that particular kind of shrinkage. You can have a general shrinkage, and you can have a general, like kind of semi-estimator in the whitened domain. Okay. OIS is just simply doing the 1 over S. And if our semi-OIS with the population covariance in the whitened domain is the ridge in the whitened domain. And you can also look at the truncated SVM. And Wins was able to get some analytical results for this in the whitened domain for a general form of H, which is bounded. So you have to assume that our predictor doesn't have to be Gaussian, but has to have this decomposition. Okay, so X has to be, if you do the inverse, go this way, has to start with IID Z's, doesn't have to be Gaussian. Gaussian is a special case with false moment. This is very much the technical condition we took out from the random matrices literature, right? This false moment and stuff. Okay, I think probably can be generalized, but just because existing random matrix result needs this kind of decomposition, that's why we have these kind of conditions. And you have a IID Z, and you do a kind of a transform through the square root of population covariance, and we define the signal to noise ratio, and we want the signal to noise ratio to be kind of stable, and N and P can go to infinity to a limit, can be larger than 1, but it's kind of the same order. That's the large P little n case. And then you can derive this kind of analytical expression. So this is model error. This is very much the same as mean square prediction error. Has a limit related to signal to noise ratio. And FR is the Panchenko-Pascal law, which is the limiting distribution of the eigenvalues of the sample covariance matrix under those conditions. That's just, and with the expression. Okay, and we need to use both the eigenvalue distribution result, and also we also needed some eigenvector result. Conveniently, it came out from the random matrix literature last year by Bai and other people. I'll say a little about the proof if we have time. So we're basically using very much the results from random matrices to get this result. And from that expression, you can show that in the Y domain, in the Yton domain, then this is the best asymptotically optimal kind of shrinkage. That's exactly the form using population covariance. It's not rich, and it's better than OIS, so that's in that class of models. And so we can say that it's asymptotically better than OIS. No, I'm sorry, it doesn't cover rich in the original domain. This is the rich in the Yton domain. And it's kind of reminiscent of the shrinkage factor in the James-Stein estimator. And we can estimate this SNR pretty easily by running some pre-processing method and get basically the parameter tuned, or you use cross-validation. So now back to, remember we motivated ourselves with the FMR problem and went away and did some mathematical calculations. Now check reality, right? So we're happy with the random matrix because picking out, we learned something with a problem, it's better to learn. And now really does it work? So we use the 5-fold cross-validation to select the parameter. This can all be fine-tuned because this was done like in the past week or so. So we didn't, it's just a first pass. And we run L2 boosting, as I said, very much, I think Lasso will give the same result. It's their favorite measure now in the Galan lab. And then we used the semi-versions. And we pre-selected the features by correlation. Okay, just the first part. We use the correlation, just individual predictors with the response. Pretty simple-minded, not as fancy as Peter Bingman talked about. And then we tried other methods. After we realized the penalization form, and we felt like the one we had theoretical result is not that natural. And also talking to people in the lab, it seems like the sigma inverse would be the more natural one. And if you do 0, you get ridge. So we think that maybe ridge will work. If ridge works, then it is still a method, but is that semi-superior learning or just regularization? Right, so we tried 3 different sigmas. 0 gives you ridge, equal 1, that's the one we have theoretical result from the population matrix. This is one also from population matrix, but use the inverse of the covariance matrix. That seems more natural. You're putting more weight on the low frequency than the high frequency. And that's what the lab people would say that we'll go for this one. They have good intuition, as you will see. I think we didn't see that because we started with more from the sample covariance point of view. After we did this, it was pretty clear. We were wondering about that to ourselves. It doesn't seem to be the best choice. Okay, so here's the result. We got 11 voxels from the lab. Actually, I was using this data for my upper division undergraduate class on general linear model. We did boosting. And then for the undergraduate, the lab gave us the best voxels for prediction because they want things to be relatively clear. And we haven't had time to get more data, so we're just using the data already in our hands for this, but we need to get more data. This is the best performing voxels using L2 boosting. Okay, so OAS, semi-OAS, ridge, and semi-OAS with inverse, they all based on the 500 pre-selected features. Okay, we did dimensionality reduction just like that. So they all based on the same 500 features selected by correlation. And L2 boosting is running L2 boosting with 10,000 features. Okay. And this is on the validation data set 120 samples, the correlation of the prediction with the observed, which is average cross trial of like 10. Okay, so it's better than 1. You can see that OS on average doesn't do very well. And our theorem is not wrong. We only compare with the OIS, right? So the SAMA OS does do better. And it's not trivially better, it's there. However, this regularization doesn't seem to be the right one for this data set, right? As we suspected too, because from the Bayesian interpretation, you're putting more weight on the low, high frequencies. Very rare, unless some subject matter is the case. So for L2 boosting, that's the benchmark the lab is doing. So we're able to use rich or SAMA OS with the inverse match the L2 boosting performance in terms of prediction. Okay, so our theoretical, we try to get a ridge, we haven't gotten there for the calculation, so it would be nice to get theoretical calculation to show that actually this is better than that. But we might introduce some assumptions, I think, to get there. Because as you see, if we have the other way around, happens to be beta is large for the high frequency components, then this probably will be better. But this is not for this data, right? But so we need to introduce probably more condition to really compare this with that. This is just regularization. So the question is this semi-supervised learning unlabeled data, or this is just regularization? We need to go back to talk to the collaborators. And let me just show you, we try to understand a little bit. Remember my features were Gabor with different locations and with different orientations. And so we just look at all the features and the locations, and we plotted the sum of all the features at the same location, the magnitude. We don't have ongoing information here, just for a first pass where they are. And you can see that L2 boosting is picking up things relatively, this is 2, but some location and then can be all over the place. Okay, and the 500 pre-selection, because using bound correlation, is very concentrated on one spatial location. It's just most of the important, they're correlated, and most of the important features are same location. So you could say that maybe this is just speculation that the one voxel is concentrating on a particular spatial location. We need to go back. We right now don't have information where this voxels sit on the visual pathway, because there are some cells and some locations can specialize to spatial locations. Right now, we don't know exactly how this 11 voxels sit on the visual pathway. And if you put them side by side, you can see that, they do coincide. This you see, this now you seem to see two bumps, and this you're a little bit there. So they're not completely inconsistent, but this you will say coherent, but is that coherent the right thing? Or actually this is more informative, because this is, of course, you individually doing correlations. Of course, they all correlated with Y, they all correlated with each other. This is probably the strong ones. But are this actually more interesting, especially this one and this one? The red and this one, the rest is pretty consistent in terms of location. So this is something we need to go back to talk to collaborators and to see how they think. They might still like the L2 boosting, I think. But the question is, the methodology in the lab is very predictive now. But now at least we present a question for them or for us. You have two methods which match prediction performance. And if you want to interpret, the subject matter will come in, or we can do more statistics and to maybe compare them without having to depend on qualitative subject information. So I guess I'll finish early. I'll show you a little bit about the proof, maybe. So we have been basically, because the lab has been doing linear model in the transform domain, we only have the 11 best voxels, and we need to get the not so voxels. But also maybe we'll see a difference, because the 11 voxels were picked based on L2 boosting performance. They were the best for L2 boosting, so it's better suited for that method. And we matched the performance. So the possibility that maybe we can do better than boosting, hopefully, for other voxels. They have thousands of voxels. As I said, the data was obtained because I wanted to use in undergraduate class, and this I will do something easier. And in terms of features, we pre-selected 500. We could try 100, 200, 300. The average number of features selected by L2 boosting is about 120. smallest one is like 60 something, the big one is like 200. So they're sparser in terms of just, is that the right number of kind of complexity of the model, right? Because boosting is very much dependent steps, is that should just count for terms, right? So there's a question there. And can we interpret the two slides I show you? We should also look at the angles and show the scientists and which one they think. Prediction-wise, before is that you cannot talk to them really if you don't match the prediction performance. They really want prediction performance. But now we match the performance, which one is more reasonable. And back to now we have some reality check, at least for this problem. Can we show something, compare these different methods also theoretically, but maybe with actual assumptions about where the betas are. And the interesting problem in the future is there have been work on natural images, like Stanford has a group by Carl Carlson, and it's the topology people. They think that they find Klein bottle in this image space, right? So is there something we need a metric, right? We cannot just do things with topological, entities. But people believe that the natural image space is not just random sample from the whole image space, right? You have wavelet modeling, or you have hierarchy modeling. So there is structure. Is that manifold, or is that cluster, or is it a mixture of both? And shall we, possibly the different parts of the space maybe entertain different linear models? Or we might even go on linear models. So those are the questions to be explored. And we probably need a bigger database. So in the simulation, in the experimental result, we use all the images from the database. But it's only 1100. And with 500 by 500, it's still not a lot to estimate the covariance matrix. Right? It seems a lot, but when the covariance, we have 500 by 500, so you have still underestimation. You might still have the problem. That estimation needs to be regularized. Right? So the theoretical result is about population covariance. And the unlabeled data, the data size, base size we have now, probably still give not a good estimate of that population covariance matrix. So that we haven't explored it either. And I think I'll just stop here for 5 minutes for questions. And the first part, the paper will appear in Annals Statistics already at my website and also at the Annals website. And we'd like to thank the Galan Lab, who has been very patient with us to answer questions. And I was there for the whole year, but bugging them. But I think I was also very friendly general consultant, so I think they also got something out of me. But they're really willing to collaborate, and especially Thomas, Nazarens, and Kendrick, very helpful for this project. Thank you.
Thank you, Ben.
Ben, to what extent do you have a strong prior model for what the brain image ought to look like in these experiments?
I mean, about the image part or about the relation part?
The image part first, because I think that leads to the relation. But
well, I mean, for the low visual areas, people pretty sure this Gabor stuff is what's happening physically with the brain. But high level, especially when you go to the part where there's attention, the feedback is not here. People know that for specific, for certain cells, they only respond to faces. There was just a paper in Science I was reading on the plane that showed that we're so specialized to animals, faces, that there's very specialized cells. And then one thing about the spatial, for the voxel, for one thing, can you assume the voxels next to each other have similar responses? And then the answer is probably not, because you think that the brain needs some redundancy, that you don't want the same functional, voxels or whatever cells to be together, right? To be, there has to be some redundancy. So the many conventional spatial kind of assumption might not be here. That's why we don't want to, we can learn about the spatial relationships, but it's hard to put just a spatial process with smoothness, local smoothness. We're not, feel worried to move there. But for the image stuff, I think actually Manford and Anne also did work on the high order image statistics. I think the Stanford group followed up on that, and with this Klein bottle stuff. But still, I think it's small patches. So we have much bigger patches. So they have 9 by 9 or something like that. So it's small patches of images. And then David Field was going to write a paper on manifolds on images, but the paper was collaborating with student at Galan's lab. But that paper just hasn't been material, it has been in the working for a couple of years. So this talking about manifold and structured. And for the image compression or processing group, a field, you have wavelets, you have then like a hierarchical model on the wavelet coefficient, and recently Michael Jordan's group also did something to do with the diversity process, try to learn global structures, right? So there's a lot of that. So in theory, we'll be exploring that too. But right now, and computationally, whether that's feasible. So the linear part is in kind of the first step we took at it. But now maybe just regularization, but maybe there's more to it. So we're unsure at this point. But seems like the unlabeled data should help, the structured image should help. But we're definitely far from there yet. Yeah. Yes, Dennis.
In your study of procedures based on sort of the ordinary least squares theme, I was wondering if you considered partial least squares, and if you did, what was your reaction?
We haven't tried that. That's definitely, it's kind of not quite the same boosting, but it's like refitting. Actually, for the class project, students didn't do partial, but they did something like forward selection and refitted the selective order with least squares and give very similar results. But we haven't specifically tried partial least squares. My guess is that the lab basically, when we had the meeting, tried to set up something formal because the data, that they made it very clear that for the linear stuff, they feel like it's going to be very hard to beat the L2 boosting in terms of prediction. But they're very sure because they have very bright people who work on this year round, right? And we just kind of dab on this. And so their thing is nonlinearity. But they were interested in the unlabeled data, but they were not surprised at all we couldn't beat them. So, but I think the nonlinearity is, and also maybe nonlinear transform of some of the features. They kind of want some novel features which is not through this Gabor stuff. And they are pretty much don't know where to go. So nonlinearity is very much on their mind. And both, I think the unlabeled data in theory can also be helpful.
Other questions? Well, since you...
I was just going to ask about the image is obviously collected over time, and so are things happening differently at different times in the with relation between the y and the x's?
Well, they're doing random sampling right now. So that's why it's more IID. But when they have like natural movies, right, and that will be really, we have to do time series kind of.
Even when they show an image, something's happening over time there. It's not just one.
Well, definitely in the high level, you can think that there's an attention process going on, right? There's some innate process going on, and then we probably should look at that's.
In different places, things happen.
Yeah. We would like to also start asking a DAI for that. We would like to do a little bit like explore data analysis or something, right? But it has turned out to be not easy. And the lab, they do some plots, but the volume of data is so huge that just simple fitting a lot of the modern problems like that is, we did look at some of the residuals. And we did spot some nonlinearity. But then it's only, based on one feature. And then how warp that in, will affect other features. It's hard to know. We didn't really bring in a lot of big improvement. So the first thing Vince actually tried to use the fitted values and do a square of that because we saw a little in the residual plot. But we didn't really address question, look at the time. In theory, there's also, at the neuron level, at least there's this refraction period, right? So you will have no response. And this is, we haven't looked into that, but that's something could be explored. Right, yeah.
Let me take the chairman's prerogative and make a comment on this unlabeled data point, just just in terms of intuition for those of you that don't know it. So why do the unlabeled x's matter in building a regression to relate y to x based on the labeled data? Fundamentally, if you believe the world is the following, that y in fact relates to some things you don't observe, latent factors that underlie x in some lower dimensional space typically. The unlabeled x's give you information about the joint structure of x's, okay, and which sort of allows you to improve or refine the estimation of these underlying latent factors in the labeled cases. And that's sort of the backwards loop that brings the labeled data, the unlabeled data x into the regression on the labeled cases. And I think what Bin has at the end, when she realized that putting sigma x was wrong and she needed sigma inverse in her prior, because the Bayesian intuition told her that it was wrong, is moving into a class of models, latent factor models, which explicitly regress y on latent factors underlying the distribution of x. So all future x's will help you learn about that latent factor model and thereby feed through into your regression. Is that right?
I have to learn more about latent variables.
So that's one of the examples, and you kind of reference our paper, although I couldn't figure out whether the symbol at the end of my name was an exclamation mark or an L. So let's thank the speaker again, very stimulating.
Typo.